So we're going to discuss in a little more depth the fundamental theorem of calculus. We have already seen what it is, so let's recall what it says for us. So basically it says that if an antiderivative for f lowercase is f uppercase, and we suppose that f is little f is a continuous function, then the integral from a to b of f of x dx is equal to f of b minus f of a. And from now on, we will have a new notation for this. We're going to denote this by f of x, and we're going to draw a straight line. We're going to put a little a and a little b, and that's exactly what this thing will mean. So it will mean exactly this. Okay, so these two things are going to be the same. One of the questions that we would like to answer is how exactly did this theorem come to be? Meaning, we have two processes: the process of computing the slope of the tangent to the graph of a function, in other words, computing derivatives, and the process of computing areas. What exactly could have inspired people to bring this together in one theorem? First of all, we should mention that this formula here is known as the Newton-Leibniz formula. And it's actually something that has been contested and disputed over the years as to who should take credit for this theorem, which is pretty much one of the most important theorems in the history of the human race, and that's not really an exaggeration. But we should try to understand that the motivation of the mathematicians of the period when this theorem was introduced in this form was pretty much to express the physical world in terms of equations. And of course, one of the things that they wanted to do is study motion. So when one studies motion, we have the following situation. So let's say that we study the simplest case, which is motion that takes place on a line that has been numbered so as to be able to identify positions. And you have a vehicle that is moving on this line. To be more precise, you could think of a point mass. In physics, we do like to talk about point masses that pretty much do not have any dimensions. But in any case, let's say that x of t is the position of this moving object time t. Then it turns out that if we take the derivative of the position function, what we obtain is the velocity. And the velocity is pretty much a word which is associated very closely to speed, but it formally differs from speed in the following way. If the motion is done from smaller axis to larger axis, so in this case, from the left to the right, then the rate of change of the x is going to be positive because we're going from smaller axis to larger axis, so the velocity is going to be positive. If the motion is taking place in the opposite direction, from the right to the left, then we go from larger axis to smaller axis, and the velocity is going to be negative. Now, of course, if you're in a car and you're driving in your car, you just see the speed, and the speed can be considered to be the absolute value of the velocity. So for our purposes, we can restrict our attention to just motions that go from the left to the right, so the velocity is positive. And here we should also mention something that is not directly needed for the fundamental theorem of calculus, which is that the second derivative is going to be the acceleration. Okay, but we're not going to need this. Now, we should say something about the case of uniform motion. So what do we mean by uniform motion? Uniform motion is when the velocity is constant. And in that case, if we were to take the velocity and sketch its graph with respect to time, then we would see a straight line, right? From time 0 to whatever time t we want to go. And in the case of uniform motion, the area of the rectangle that corresponds to a given motion is just the distance. So the value of the motion, I'm sorry, the value of the velocity times the time that it took to travel, let's say that it's uppercase t, that will be the distance. So we have the principle that in the case of uniform motion, time times velocity is equal to the distance, which of course begs the question, what is happening in the case of non-uniform motion? So in the case of non-uniform motion, which is pretty much what we have in everyday life, you have an object that starts moving. It starts from velocity 0, it doesn't move, then it keeps going, its velocity fluctuates, and we get such a curve for the velocity. So if we apply the principle of the method of exhaustion and we subdivide the interval of time into very, very small intervals, then we can suppose that on each of these intervals, the velocity remains constant. And that means that we have uniform motion, approximately uniform motion, which means that we can take the little rectangle that corresponds to, I don't know, it could be 1/10 of a second time interval to be the distance that was traveled during that interval. And if you keep applying this for different intervals, then eventually all these areas of the rectangles add up to something that should be pretty close to the distance that was traveled by this moving object. And as the length of these intervals goes to 0, we should get the actual distance, which means that now the area between the graph of the velocity and the time axis acquires a simple interpretation. It's the distance. And what is the distance? The distance is the position you were at time t minus the position that you were at time 0. So this is the integral of the velocity from 0 to t. And if you look at this thing and take into consideration that the velocity is nothing else but dx over dt, then you can see that the relation between the function that you integrate, which is really this dx over dt, and the function whose difference you're taking is the relation between a function and its antiderivative. So that's the fundamental theorem of calculus. So in other words, if somebody asks you, how can you logically deduce the fundamental theorem of calculus? The answer is just consider the diagram of velocity with respect to time. And if you realize that what is contained in the, what the area represents between the graph of the velocity and the time axis, then you will have that. If you realize that it represents distance, then that's the fundamental theorem of calculus. Nothing more, nothing less. And of course, we should say here that when one tries to prove the fundamental theorem of calculus, other means have to be used. And there are many, many different proofs of the fundamental theorem of calculus. Namely, you will have proofs that use the mean value theorem. But for us, it's important to understand how this emerges as an answer to the question of expressing, of understanding the motion in terms of equations. So from the point of view of using now the fundamental theorem of calculus, we can have simple situations that we have already seen. We can extend them a little more. So let's take the integral of cos x from 0 to pi over 2. And the question, as usual, is the derivative of what function is cosine x? And the answer is going to be sine x. And this is going to be sine x from 0 to pi over 2, according to the new notation that we introduced, which is going to be sine of pi over 2 minus sine of 0, which is 1, minus 0, which is 1. Or let's do another simple example. Let's say we want to find the integral of dx over x. When I write dx over x, that means 1 over x times dx from, let's say, 1 to 2. Again, I'm going to ask the antiderivative of what function is 1 over x, and the answer is certainly ln of x. We will see later that this can be extended a little for to include negative numbers, but for the moment being, we're just interested in positive numbers. So we're going to have ln of x from 1 to 2, which is ln of 2 minus ln of 1, ln of 1 being 0, that gives you simply ln of 2. And that's another example of an integral. And we can see that in this whole discussion, we need to constantly ask the question of what the antiderivative or an antiderivative, to be a little more precise, of a given function is. And since this is the most constantly occurring question, it only makes sense that to actually introduce a new formalism that computes antiderivatives, that actually focuses on antiderivatives. And that's the formalism of the indefinite integral. So the indefinite integral, indefinite is as opposed to definite that has limits. This one will not have limits. And unfortunately, one might say that the choice of terminology and symbol could be a little misleading, but what we mean is pretty much by definite integral is the antiderivative or an antiderivative or all antiderivatives. This is the fun part. How can we? So the symbol that we have is that the indefinite integral, so again, notice that I'm not putting any limits of integration here, is going to be an antiderivative for little f. But here's the problem. If I plan to use this as a symbol, this symbol should mean the same thing for everyone. But if you ask me what is an antiderivative for cosine, I will tell you sine of x. Well, somebody else might tell you sine of x plus 3, and somebody else might tell you sine x minus 7. So you can add pretty much any constant. So the idea is that we want to have a notation that pretty much includes all possible constants that one could could add to a given answer that could be provided. And that's why we put plus c. And here the understanding is always that the derivative of f prime, the derivative of f uppercase is f lowercase. And this is what we write. So you can see that structurally speaking, the definite integral and the indefinite integral are two completely different objects. The definite integral is a number, the indefinite integral is a function, and to be more precise, it's infinitely many functions that differ by a constant. So for example, with what we just introduced, we could write that cosine x, the antiderivative of cosine x, or the indefinite integral from now on of cosine x is sine x plus c. So there's no need to put this annoying question mark prime and things like that. So we can give these antiderivatives, and we will always understand that once we find this, the thing that will go into the fundamental theorem of calculus is going to be just the part without the c. And that's the formalism of the indefinite integral. And at this point, we should say that the that there are some tricks. So for example, if you have x to the a, then the indefinite integral of that will be x to the a plus 1 over a plus 1. This is true for any a different from -1. And you can play all sorts of games. So for example, if we were asked to find the indefinite integral of e to the 5x dx, then it's not that immediate. I mean, how do you find the antiderivative for e to the 5x? Well, there's this little principle that we can use that if you find a function whose derivative is a constant multiple of the function that you're trying to integrate, that you're trying to find the antiderivative of, then you could anticipate the presence of that constant and start instead with 1 over that constant times the function that you guessed, and that will give you simply the function that you were interested in. So the answer here would have been 1/5 e to the 5x. A similar thing, if we have cosine of 7x, here you could try to take the derivative of sine of 7x. You will see that the derivative of sine of 7x is cosine of 7x times 7. So this would be 1/7 sine of 7x plus c. And we will have something like x cubed e to the x to the 4th. Here you could try to look at e to the x to the 4th. What is the derivative of e to the x to the 4th? And you will see that it's e to the x to the 4th times 4x cubed by the chain rule. So you're finding pretty much what you have here with the exception of this 4. So what will the antiderivative be here? 1/4 e to the x to the 4th plus c. We're going to formalize this much more when we introduce the method of substitution, but we can see that there are plenty of things that we can do from a very elementary perspective. Now, obviously, the fundamental theorem of calculus sets us on a trajectory of finding antiderivatives. A good question that comes up is, do antiderivatives exist? And there is a theorem which is usually called the first form of the fundamental theorem of calculus that tells us that antiderivatives exist for all continuous functions. So it says that if f of x is continuous on the interval I and a belongs to I, then the function, and this is a very unusual function, you've never seen anything like this. It's the function defined from representing the integral from a to x, meaning it's the area if we use t-axis instead of and y-axis instead of x, so imagine this is your function, this is a, let's say, and then you have a point x. And what you do is you take this area, and that's what f uppercase of x is. So as x varies, and remember that x could even be on the left of a, and this is where the fact that we can have a definite integral with lower end point larger than the upper end point, upper limit kicks in. Then this function given by this formula is an antiderivative of f of x over I. So what this theorem tells you is that all reasonable functions do have antiderivatives. So trying to find antiderivatives is not a meaningless task. It always exists. However, we have to realize right from the beginning when we start this journey that in general it is much more complicated and sometimes impossible in simple terms to find antiderivatives of some functions. So we do have rules that enable us to pretty much take the derivative of any function that we might want, but going the other way around. So finding a function whose derivative is one that we have at hand is not something which can be taken for granted. And that makes the process of integration much more challenging, much more interesting, and we will try to look at some examples of it. So we have now everything in place. Our goal is to compute definite integrals. We understand that we have to go through antiderivatives whose existence is ensured by the theorem that we just gave, and we create the formalism of the indefinite integrals that has as its sole goal to help us find those antiderivatives. And that's all. Thanks for watching.